Hi there, I'm Dr. Vivian Lowe. Welcome to vlmd Rounds, a podcast on medical science and tools to optimize your health. Many people have written to me requesting certain topics, and quite a few people have asked me to talk about Alzheimer's disease. I have hesitated and kind of put that off quite a bit, simply because I think that these big topics like Alzheimer's and atherosclerosis, for example, they're such huge topics. There's so many factors involved, and it's really hard to put everything into one episode. So that's been quite daunting for me to try to cram everything into one episode. But I thought that I would just make a start towards Alzheimer's a little bit at a time and, kind of slowly inch my way into the various aspects of the disease. I want to point out that in my attempt to just lay an overview picture of Alzheimer's today, it's going to be a very, very broad survey, very broad view. There are going to be many things that I'll be skipping just because I'm trying not to get too involved in the details and go down some rabbit holes, and then I'd be trapped there for hours, right? And I don't want to trap you in rabbit holes as well. So we'll just take it a little bit at a time, and we'll maybe explore different aspects of Alzheimer's in different episodes, bearing in mind I'm just going to paint a very broad picture and ask some very general questions in this episode. All right, I hope I can do this in one take. Let's see. Wish me luck. Let's go. All right, let's start with general, information about Alzheimer's. It's the sixth leading cause of death in the US and affects about 5.8 million people in the United States, but about 15 million people globally. And of course, Alzheimer's is age-related. So if you're in the 85 or older group, then 50% of people in that group have Alzheimer's, very much related to age. Women more affected than men, and this is even when we adjust for age because women tend to live longer. So even after adjusting for other confounding factors, it seems like women are more likely to get Alzheimer's than men. And nowadays, with people living a lot longer, obviously there's a lot of concern about the development of Alzheimer's because, obviously you want to have a vibrant, functional life. And so now the focus is not just on the number of years that you're alive, but the number of good years, right? So your health span is really important. With Alzheimer's, it tends to be a gradual onset of symptoms, and you might notice, some decline in executive function. So people maybe have trouble making decisions or managing their finances, making poor business-related decisions, for example. And of course, then there are deficits in memory and learning. And in the later stages, we see more problems with language, and also behavioral problems tend to crop up. And there are also sleep disturbances that are associated with the disease. So with Alzheimer's, it's famously associated with some dysregulated proteins in the brain. I think everyone has heard of amyloid beta, right? Which are these proteins that they're able to form plaques in the brain. And the formation of plaques tends to occur years before symptomology, before people even develop any signs or symptoms of the disease. And we've noted that people with higher risk for Alzheimer's, and we'll discuss that in a bit, people with higher risk for Alzheimer's actually have more deposition of these amyloid beta plaques, and it's sort of an accelerated deposition of those plaques way before the disease symptoms appear. Now, the thing about the amyloid plaques is that tends to happen, well before you notice symptoms, but once you have amyloid plaques develop in the brain, the plaques themselves seem to promote the seeding of tau proteins, and these are hyperphosphorylated tau proteins that form these neurofibrillar tangles inside the cells in the neurites or in the cell bodies of the neurons, right? And it's really the formation of these tau proteins and aggregates in the neurons that are associated with disease progression, with symptoms developing, and also, neuronal destruction and cognitive decline. So the time course is such that well before you ever have symptoms, again, you start to see the accumulation of these amyloid beta plaques in these are extracellular in the brains, and this promotes tau seeding and hyperphosphorylated tau neurofibrillar tangles accumulating inside cells. And once you have that tau seeding and the formation of those aggregates inside cells, very shortly after, you will see disease symptoms and cognitive decline, and the tau really matches with the symptomology there. Okay, Alzheimer's disease, even from the very beginning, Alzheimer, who this disease is named after, had noticed that there was a marked sort of microgliosis in the brain of patients who had this disease. Now, microglia are the resident tissue macrophages in our brains. I have mentioned this a few times. It's probably worth mentioning again. I have a talk on YouTube you can access. It's called the Magical Mystery Macrophage Tour, and it gives a very, very basic general overview on macrophages. In that episode, I do talk about resident tissue macrophages, of which microglia are one, and they happen to be the tissue macrophages that are found in your brain. And so they occur during embryogenesis, and they seed the brain from those very early days, and they tend to be involved in homeostatic housekeeping processes in the brain. So just cleaning up brain debris and keeping the neurons sort of healthy, right? But they are the primary immune cells in the brain. And of course, there are other macrophages that will get into the brain. But when we talk about the tissue resident macrophages, then we're really talking about microglia. And it's been noticed, for a very long time, that in brains afflicted with Alzheimer's, there's this increased microglial action. Microgliosis is what it's referred to. And people have noted this and realized that somehow there's an inflammatory response in the brain that's associated with the development of Alzheimer's disease. Now, I think when you talk about Alzheimer's, it's inevitable you talk about the risk factors for Alzheimer's, and the biggest risk factor would be in ApoE. So let's take a look at that. ApoE is an apolipoprotein. I discussed this in the lipoprotein episode, and you can go refer back to that. So we find ApoE generally in the body in VLDL and chylomicrons and LDL and HDL. So you find them in the different lipoprotein species in the body, and it also binds to LDL, receptor, LRP, VLDL receptors, and also the scavenger receptors, SRBR1. All right, so that's apolipoprotein E. In mice and in other animals, there's just one type of ApoE, but in humans, there are actually 3 isoforms that differ only by 1 amino acid, either at position 112 or 158, okay, depending on which isoform. So we have isoform E2, isoform E3, and isoform E4, and really E2 is it's seen in about 7% of the population. E3 is the most common allele, seen in about 78% of the population, and E4 in about 15%. Now, the different isoforms confer different risks to cardiometabolic diseases and also Alzheimer's. So one copy of the E4 allele will increase your risk for Alzheimer's 4-fold. All right, so that's pretty significant. However, if you are homozygous for E4 and you have 2 copies of E4, then that increases your risk 12-fold. So that's a whopping increase in risk. E2 actually is seen to be associated with decreased risk for Alzheimer's. So you have a 50% decreased risk if you have E2, all right? But the E4 is the one that most people are worried about. Okay, and you know, we find that ApoE tends to be highly expressed in nervous tissue and when we have any kind of neuronal injury. Brain ApoE is made primarily by astrocytes and also sometimes in microglia. And it actually binds strongly to amyloid beta and can impact the aggregation of amyloid beta in the brain. So if someone is E4 homozygous, that means they have 2 alleles for E4, they have greater than 60% of them have amyloid beta deposition in their brains between the ages of 50 and 70. Okay, and that's much increased compared to people with other isoforms. So again, you have this increased risk for Alzheimer's, and that's reflected in the increased deposition of the amyloid beta plaques. Very briefly, I want to mention that after ApoE, the other risk factor for Alzheimer's would be TREM2, and TREM2 I'll talk about in a little bit when we go to the microglia again, okay? Back to the ApoE4, it tends to bind amyloid beta the least, okay? So it's not very good binding capacity to amyloid beta. But then binding is really not so much associated with the amyloid beta burden. And now most people think it's actually that the amyloid beta is competing for receptor sites for its clearance, right? So E4, for example, binds LRP1 and tends to compete with amyloid beta for that binding site. And therefore that decreases amyloid beta clearance. Okay? So that seems to be the association between the isoforms of apolipoprotein E and, you know, the ability to clear amyloid beta in the brain. All right, now let's go back to the microglia. So we're going to be going back and forth in so many directions because it's really hard to talk about Alzheimer's without touching on all these different points. All right, so back to the microglia. Microglia are the only cells in the brain that express a receptor that's called triggering receptor expressed in myeloid cells. Okay, triggering receptor expressed in myeloid cells, or TREM, all in caps, TREM, TREM2. Okay, so now that's expressed in different areas of the body, but in the brain you only will see TREM2 in microglia. Okay, so that's very important. And this TREM2 is actually a surface protein attached to the cell membrane, single pass protein there, and it's very much involved in signal transduction and immune function regulation. So what we've noted is that when you look at the amyloid beta plaques, there is definitely a difference in the animal models that were studied that had knockout of TREM2 in the brain, okay, in the microglia. And what that was that if you knocked out TREM2, you had plaques that were just more diffuse and that sort of seeped more into the parenchyma of the brain. So it seemed like those plaques were more spread out. And there were less activated microglia associated with those plaques, okay, with the amyloid beta. So again, since TREM2 is associated with immune function, when you knock out TREM2 in the brain, then we see that actually there's less microglial activation, and as a result, those plaques seem to spread out more and kind of diffuse themselves more into the brain parenchyma. So the thinking is that TREM2 allows the microglial cells to be activated and to bind to the plaque to limit the plaque, such that, you know, it doesn't kind of spread itself out in the brain tissue. Okay, so in the amyloid beta stage, we see that the microglial action is somewhat protective because it's trying to limit the spread, the extent of the spread of these amyloid plaques, okay, through the activation of TREM2. Now, interestingly, if you look at ApoE deficient mice, they also tend to have more diffuse plaques, and that means that there's more spread of those plaques, widespread spread of the plaques into the brain parenchyma. All right, now we had mentioned earlier that the amyloid beta plaques lead to greater seeding of the tau proteins, right? And, you know, we get more of this hyperphosphorylated tau tangles inside the cells. And that is what is associated with neuronal loss and symptoms of dementia, okay? So although it's not actually the amyloid plaque themselves, the amyloid plaques somehow promote the tau, and the tau pathology is what brings on the destruction of neuronal cells and also the cognitive decline. So in studies using mice models of tau pathology, right, these mice were actually more prone to developing lots of aggregation of tau in their brain cells. TREM2 deficiency in those circumstances actually protected the brain, right? So if you didn't have TREM2, you protected those mice from brain atrophy. So the idea is that TREM2 actually, that signaling of TREM2 leads to activated microglia in the amyloid beta phase that is actually protective and limits the spread of the plaques. However, when we get to the late stage and we already have tau seeding, right? Now the TREM2 signaling will activate microglia, and we have a bigger inflammatory response and more inflammatory cytokine signaling. And as a result, this is going to cause more destruction of neurons, causing neuronal destruction and death, right? And therefore, brain atrophy. So really, in the tau stage, the whole idea there is that you don't want to have the microglial activation. You want to decrease that so that you have less of this inflammatory response. And in, again, studies using these mice that tend to have tau pathology there, they had these E4 mice models that were knocked in, and those mice actually had increased atrophy in the brain. However, if they actually were able to deactivate those microglia, then there was no brain atrophy at all. Okay, so there were they were given this drug that is actually able to knock out the microglia in the brain. And as a result, even in the E4 mice models that were prone to the tau pathology, they didn't have any brain atrophy at all. Okay, so it protected them once they limited the action of microglia by just knocking them out. Okay, and incidentally, in ApoE knockout mice, right, with this tau pathology, they too had much decreased atrophy in the brain. And it turns out that TREM2 and ApoE are related, and actually TREM2 binds ApoE. And it binds ApoE4 especially well. So the thinking is that in the E4 circumstances, there's actually increased microglial activation and more inflammatory or pro-inflammatory response in the brains of people who were carriers of E4. Because again, there's stronger binding of E4 to TREM2. All right, so we've talked about, the microglia and how in the amyloid stage they can be protected by limiting the plaques. But by the time we get to the tau stage, actually the microglia are going to be activated and cause more pro-inflammatory response in the brain, which exacerbates the neuronal destruction and brings about the cognitive decline. So now I am going to move over and talk about brain cholesterol. Trust me, this all links up, but just trying to tie a lot of these things together. So your brain is about 2% of your body weight, and yet it holds about 25% of the total cholesterol content in your body. So that's a lot of cholesterol, and 70 to 80% of that cholesterol is found in myelin. All right, so the myelin, this would be the fatty sheath that insulates axons, very important for nerve conduction. Okay, so a lot of this cholesterol in the brain is actually found in myelin. It's so important for the brain that, guess what? The brain doesn't want to outsource cholesterol production, so it makes its own cholesterol. And brain cholesterol synthesis is highest during embryogenesis and also in childhood, and this coincides with the period of maximal myelinogenesis. So as you're forming a lot more myelin in the brain, you're going to have a lot of brain cholesterol being formed, and this is done by both neurons and glial cells in that phase. But by the time you become an adult, okay, so in the adult brain, really cholesterol is only made by glial cells. And you don't have really any production of cholesterol by the neurons. So that really the neurons are dependent on delivery of cholesterol to them via lipoproteins so that they can repair and maintain their membranes. So again, like in other cells in the body, cholesterol is also concentrated with sphingolipids in these lipid raft domains that are very important for cell signaling and neurotransmission. Okay. In terms of the cholesterol in the brain, we have to now talk about the blood-brain barrier again. Okay, so with the blood-brain barrier, we know that this is where we exclude a lot of what's in the blood from the brain tissue, right? And anything that passes through to the brain has to be lipophilic and also maybe be able to be transported via certain carrier proteins, for example. So we have the blood-brain barrier. We also have the blood-CSF barrier, okay? And this is just another part of the brain, the choroid plexus, right? And in that area, let's just say the blood-brain barrier is slightly leaky, and so there are some substances that can get through into the brain at the blood-CSF barrier. Okay, now, ApoB lipoproteins. So by that, we're talking about chylomicrons, we're talking about VLDL and LDL. All right, they cannot enter the brain, okay, because they're just separate from the brain. And so basically cholesterol from the periphery can't enter the brain. And that's actually why you have to make your own cholesterol in your brain. Now, also, since these lipoproteins from the periphery in the blood can't get into the brain, your brain has to make its own lipoproteins as well. Okay, got that? So we do have lipoproteins in the plasma, but they can't cross the blood-brain barrier and get into the brain. And so now your brain not only has to make its own cholesterol, it's got to make its own lipoproteins. All brain lipoproteins are HDL. I'm going to say that again. All brain lipoproteins are HDL or HDL-like particles. Okay. Now the CSF, cerebrospinal fluid, has very low amounts of these lipoproteins as compared to the plasma. So you have actually much less concentration of these HDL-like particles in the CSF as compared to the plasma. And furthermore, I want to emphasize that brain and CSF levels of HDL are very different. So just because we know what's in the CSF doesn't mean that translates into what's in the interstitial fluid in the brain, what's in the brain tissue itself. Okay, a lot of times we will use what we find in the CSF as a proxy for what goes on in the brain. But in many cases, that's actually not true and not a good thing to do. And in this case, yeah, definitely not, because the levels of CSF lipoproteins are different from what's in the brain. Now, brain HDL differs slightly in size and density from the plasma HDL, but the main difference is going to be the protein content. If you listened into my last episode, you'll know that whenever we talk about HDL, it's always going to be the proteins, and also the lipids, but proteins that are really important, okay? And it's one of the reasons I spent a whole episode before this one on HDL, okay? So brain HDL protein content is different. The major apolipoprotein in the plasma is what? ApoE1. Okay, that's the main one in the HDL found in the plasma. In the brain, the main apolipoprotein is ApoE. Okay, now just let's think about that. So all ApoE in the brain is on HDL. Okay, all ApoE in the brain is on HDL. And we'll just let that sink in a little bit. Brain and plasma ApoE, they do not mix. So you have to consider them as separate pools. And we know this because we've looked at patients who've had liver transplants. It's kind of cool. So what they found was that in patients with liver transplants, that their plasma E isoforms took on the isoforms of the donor liver because, you know, your plasma HDL is primarily made in the liver, also in the intestines, okay? So if you did a liver transplant on those patients, then whatever E isoform they had expressed in the plasma would be what is made by the donor liver. But in those same patients, the ApoE in their brains, in the CSF, would be actually what they had originally, their original ApoE isoform. And so we know that those two pools of ApoE do not mix. Okay, I thought that was pretty cool. All right, besides ApoE, other apolipoproteins that are found in brain HDL would be ApoE1, ApoJ or clusterin, and ApoD. I am not going to focus on those because otherwise we're going to be here all day, right? Just want to briefly say that ApoE1 is not made in the brain, okay? But it probably crosses the blood-brain barrier by endocytosis, and then once it crosses over into the brain, then it's quickly lipidated, right? So it takes on lipids at that form and is associated with HDL at that point, okay? So again, it's not, A1 is not made in the brain as far as we know, probably crosses over into the brain from through the blood-brain barrier via endocytosis, and then, you know, that's how it gets into the brain. So remember the ABCA1 transporter proteins? Well, they are very important for the lipidation of ApoE that are secreted by astrocytes, right? And what they do is that these ABCA1 proteins are able to lipidate or add lipids to the, you know, ApoE1s that ApoEs that are made in those astrocytes. And so we initially have these nascent, NASCENT, so just born nascent, lipid poor, discoidal shaped HDLs that quickly then acquire lipids via ABCA1. And then they become these small spherical HDLs. Okay, now I have here a little note here. It's really, okay, well, let's finish this up. So ABCA1 can then transfer more cholesterol and lipids to those small HDLs, and eventually those can actually become large HDLs. Now, we talked about ApoE promoting amyloid beta degradation. And this is true, especially in the case of those small lipid poor ApoEs. Those are very good at the amyloid beta degradation. And my note here is on people who were E4 carriers but were amyloid beta negative, and they actually were found to have higher amounts of small HDL in the CSF. And E4 carriers who had amyloid beta plaques, they were amyloid beta positive, they actually had more of the large HDLs found in the CSF. And that's because we think that it's really the small HDLs that are important in helping to degrade the amyloid beta. ApoE4, okay, ApoE4 has this propensity to clump and self-aggregate, okay? And this means that it tends to trap ABCA1 in endosomes. And this blocks the ABCA1 from recycling back to the plasma membrane and blocks its ability to add lipids to ApoE. And so we think that this is one way in which ApoE4 is actually, kind of changing the structure of the HDL in your brain. Now, in the case where you have ApoE4 present, right, then if you add ABCA1 agonist as a medication, under those conditions, you actually allow the formation of ApoE HDLs again. Okay, so normally with E4, you're not going to allow the formation of these small HDLs, but if you add an ABCA1 agonist in people with E4, then you are able to, again, regenerate these ApoE HDLs. Furthermore, ApoE small HDLs activate another transport protein, ABCA7, okay, and regulates it to the membrane. This ABCA7 is found in the brain. It's important for efflux of phospholipids from the plasma membrane. And what it does is it prevents accumulation of toxic lipids in lipid droplets in cells. And so when you have these small HDLs, then they are able to activate this ABCA7 to prevent these lipid droplet formation in the cells and protect it from toxic lipids. Small HDLs are also very good as antioxidants. They have strong antioxidant properties and they can protect blood vessels. And this includes the blood vessels, that are in the brain and that form part of the blood-brain barrier. So they prevent leakage and, any kind of damage to the blood-brain barrier. Okay, so right now I've just told you about brain cholesterol, and I've told you that really all of the brain cholesterol is carried in HDL in the brain, and all ApoE is associated with HDL in the brain. Okay, the reason I mentioned that is because a lot of times people ask me what they can do to prevent dementia or to decrease their risk for dementia. And it's not uncommon to hear that, we should use a ketogenic diet as an approach. Now, you should know me by now. I do use the ketogenic diet under appropriate circumstances, and I definitely want my patients to be low carb. Okay, so I have a bias towards a ketogenic diet, and I have a bias towards using low carb nutrition. Okay, that's just where I come from. But when it comes to decreasing risk for Alzheimer's, then I am not sure. I have some questions. So, if you read about the ketogenic diet in association with Alzheimer's, it's always going to be talking about ameliorating symptoms. So, improving maybe some cognitive function in patients already diagnosed with Alzheimer's. Okay, so the idea is that we provide ketones as an alternative fuel source to the brain cells that are unable to utilize glucose. Okay, and so it gives them energy via the ketones. Either you do it through a ketogenic diet, or you can give exogenous ketones to those patients. And it seems that, in some cases, it may actually hold off cognitive decline, maybe improve some of the cognitive symptoms, and provide some kind of anti-inflammatory effect to the brain, in addition to providing an alternate fuel source to the brain. However, we know that in the case of a ketogenic diet, we increase HDL. And this can vary depending on the person. Some people will just have a mild increase in HDL, and I've seen people who did not have really much of an increase in HDL. And then you have people who have really huge increases in HDL. Okay, now we've seen with plasma HDL, there's a U-shaped curve in terms of cardiovascular risk. Okay, so very low HDL, very high HDL, increased risk. Okay, but when it comes to the brain, right, and all ApoE is carried only on HDL or HDL-like particles. First of all, I don't know the effect of a ketogenic diet on brain HDL. Even if we look at CSF, that's just a proxy and not a good one. So we really don't know what's happening in the brain, in the interstitial fluid of the brain, right? In the astrocytes, for example, right? So if we're increasing plasma HDL, and in some people we see quite an accelerated increase, big increase in plasma HDL, could we be doing that in the brain? And if that person is then an ApoE4 carrier, is that a good thing? I have no idea, right? They have more E4, there's more microglial activation. Okay, and now we're not looking at people who have Alzheimer's. We're talking about risk. So where you are in the spectrum, in the time course towards disease expression, we don't really know. We could just guess. If you're pretty young, then maybe you're at the stage where if we can prevent the amyloid beta from forming plaques, right? If we can clear more of this amyloid beta, that would be good. Okay, and in that case, maybe more of ApoE, in association with TREM2 will activate those microglia, and there's a protective function at that stage. Now, if we're getting closer towards accumulation of tau, then again, that might not be a good thing, because if we have more activation of microglia, then we're going to have more pro-inflammatory signaling, causing more neuronal damage, and that is related directly to cognitive decline. Okay, so we're not talking about people who already have the diagnosis of Alzheimer's. Generally when I'm asked anyway, people want to know about their risks and how they can decrease their risk. If you're an E4 person, and then there are many people walking around who don't know what isoforms they carry, right? So is it wise to tell everyone to go on a ketogenic diet to decrease the risk of Alzheimer's? Is that true? I don't know. And that's why I think we should be very careful. It seems like it makes sense, but again, any benefits we see, we are talking about people who have already developed Alzheimer's or dementia, right? And, in people who are E4 carriers, is this an increased risk? That's a question I ask myself. I've been trying to find the answer. I don't know. And therefore, I am cautious. Okay. And so instead of telling everyone that they should go on a ketogenic diet, I definitely promote a low carb strategy. But I get a little worried with the E4 carriers. Okay. So let's do a brief wrap up. I think I raced through this because I was hoping to keep everything under an hour, and I believe I have succeeded. We started by talking about Alzheimer's and just, the disease itself, the disease course. And then we also went on to talk about the risk factors that are involved there. And we noted that the different isoforms of ApoE confer different risks to patients, right? With the highest risk being seen in people who have the E4 allele. And we also then talked about how the time course of development of disease is really important, that in the beginning you just have this accumulation of the amyloid beta plaques. And that itself isn't causing the neuronal decline, but that promotes the tau seeding and the formation of hyperphosphorylated tau neurofibrillar tangles inside the neuronal bodies and neurites, and that is what causes the neuronal destruction and the cognitive decline, right? So the plaques actually accelerate that. We found that when you have the development of plaques, there's actually increased microglial action around the plaques, and this is via TREM2, which is a cell surface receptor involved in immune signaling. And TREM2 is going to activate these microglia, and in the amyloid beta stage, this actually seems to have a protective function in that we limit the spread of the plaques and we don't allow them to seep into the brain parenchyma. However, as we go later into the course of the disease and we head towards, the seeding of tau. Now, at that point, TREM2 activation of microglia causes a pro-inflammatory profile in those microglia, and that is going to damage the neurons in the brain, cause destruction, apoptosis of the neurons, and bring about cognitive decline as a result. So when you look at this disease, you have to determine the time course. I did not go into the differences in sex. That's something else that you have to look at, right? So if you listen to my macrophage talk, I stress that when you talk about macrophages, you have to talk about origin, you have to talk about location, you have to talk about time course, you have to talk about sex, okay? Because all these things are going to impact microglial activation. Now, it turns out that ApoE actually binds well to TREM2 and especially ApoE4. So when you have ApoE4 alleles, they bind really well to TREM2 and cause increased microglial activation, so that it kind of leads your microglia to be more sort of activated. In the early amyloid plaque stage, that might be helpful, but once we get to tau seeding, it's actually going to accelerate the tau pathology and cause more symptoms, more neuronal decline. Okay, so we then actually talked about how your brain has to make its own cholesterol, really because of the blood-brain barrier and the blood-CSF barrier. Cholesterol doesn't cross into the brain, and also, lipoproteins can't cross into the brain. So the brain makes its own, lipoproteins and cholesterol, and primarily in adults, this is done in astrocytes. You have some production of ApoE in activated microglia, and also maybe even in neurons in the case of brain injury. You might see some of that, right? But primarily we're talking about astrocytes. And since lipoproteins can't cross the blood-brain barrier and your brain makes its own lipoproteins, then it's important to note that the lipoprotein that your brain makes is actually HDL, of the HDL species, okay, or HDL-like particles. And all ApoE in the brain is on HDL. And we also know that the more the smaller HDLs, the small spherical HDLs in association with ApoE tend to be protective against neurodegeneration. And it's the large HDLs that have more lipids in them that seem to be associated with more pathology in the brain. Okay, so when we talk about brain ApoE, I think the important thing to talk about is to remember is that we are talking about HDL and the types of HDLs that are formed, the size, the density, the protein content is very, very important. Lastly, talking about how we can decrease the risk for Alzheimer's via nutrition. There's been a lot of talk about using a ketogenic diet, and it may be good, but my caution here is that for a lot of people on a ketogenic diet, they increase at least plasma HDL. I don't know what happens in the brain, okay? It's really hard, and even looking at CSF HDL isn't a good approximation. So we're not clear what actually happens in the brain. And since all ApoE in the brain is on HDL, if you have a lot of HDL and you are an E4 carrier, is that a good thing? I don't know. I'm just asking the question and posing it here for all of us in the low-carb community. I think for me, the main thing is not to be dogmatic about things. Even though I am biased towards a ketogenic diet, I am biased towards low-carb strategies, I'm still very, very careful. And I've seen sometimes people advocating, oh yeah, to prevent dementia, you just go on a ketogenic diet. And that in itself is hardly individualized nutrition. It's an algorithm again. That's number one. But number two, we're not even sure if it might be harmful, okay? In the case of ketogenic diets, with people who have already developed Alzheimer's, it can provide an alternate source of nutrition for the brain cells and may have some anti-inflammatory effects. But in the preventive stage, I think before we start kind of promoting ketogenic diets, we have to think about or learn a lot more about what goes on in the brain. I think in, some of these episodes that I've done, I hope that the message of looking at different tissues, looking at different contexts is very important when you're looking at a disease, right? We kind of like to lump everything into one category, but very different things may be happening in different tissues. And we need to be aware of that and be very careful when we're considering making recommendations to patients. Okay, As I said, that was just a very brief survey, and I just gave you some of the key aspects and some of the things that I think about when I talk about or when I'm pondering neurodegenerative diseases. And there are many, many other aspects that I have not covered. I didn't go into other apolipoproteins in the brain, for example, right? And look specifically at the vascular integrity at the blood-brain barrier and some of the implications of that. I didn't look at the gut-brain axis. So there are so many things that I left out. So by no means should this episode be seen as the episode on Alzheimer's. It's just one, and it's just an introduction and a brief survey to some of the things that we need to consider when we're looking at neurodegenerative diseases in the body. Okay, write to me. Check out my website, vlmd.com, vlmd.com. I think I did it. I made this episode in one take. I was worried I would have to do a million takes, but we got through it. Check out my next live Q&A, especially if you have questions, if you want to chat about brain, HDL, brain cholesterol, ApoE, and how it impacts the brain and neurodegenerative diseases. So look in the event schedule on my website. For now, I am done with this episode, so I'm signing out from vlmd Rounds. I'm Dr. Vivian Lowe. Thank you for listening. Enjoy your week. I sing the body electric. Bye.